So in the last video, we talked about how to identify and exploit a command injection vulnerability. But those kinds of attacks are becoming rarer and rarer. The industry's kind of wised up to how dangerous it is to have user-controlled values in a format string that gets passed to system. So we have to have other avenues of attack in order to achieve arbitrary code execution. So in this video, we're going to talk about how to identify and exploit a buffer overflow. So there are a number of functions in the C standard library which, if used incorrectly, can lead to vulnerabilities. Things like stir copy or mem copy, sprintf, stuff like that. Just anytime when you're copying information from a source to a destination and the amount of information in the source exceeds the amount of space that you have in the destination. This can lead to something called a buffer overflow. So we're going to cut straight to the chase here and home in on this function that gets called by apply CGI, just like the function we found the command injection in previously. The function's called start EPI. And as always, I'm just going to start off by doing a bit of cleanup here. Even if it's a little bit overkill, it's nice to annotate a little bit just so we have a firm idea of what's going on. Oh, I also have to annotate this guy, don't I? This is all stuff that we've done previously. It just helps populate the types and whatnot for when we go back to start EPI. Now, I'm going to do some variable renaming here, just so we know what values end up where. Love how easily Binary Ninja lets you do this. Pretty easy to infer what these variables mean just semantically in the program. So we notice that down here we have 4 different calls to sprintf, and we can find buffer overflows in, it looks like every one of them, just based on just a quick scan of the logic, but I'm going to focus in on this first one, looking top to bottom. So here we have a variable, which is a local variable, it's on the stack, that is going to be the destination for whatever the result of format stringing this value, which we get from getCGI, as we know we control that value, into this string. And then the result, of course, will end up right here. So, if we go over here and we take a look at the stack view, we see here's our var 120, which, just for the time being, I'll go ahead and rename destination. You know, these two being the source, in this case, I suppose. We can see visually just how much space is given to whatever this guy's pointing to. This is actually not a void, it's a pointer of some kind. Might as well, oops, that's not right. Might as well just go ahead and update this. What the heck? Yeah, there we go. Just so that it's kind of clear that it's a pointer here. We see how much space is given over to this variable. And it looks like it's about, okay, so that's sitting at offset 120 in hex. Looks like it ends at 20 in hex. That's, what, 256 bytes? Okay, so maybe in fact we'll change this further and we'll say that this is a character array that is 256 bytes long. And actually, you know what, I'll work in decimal just to make it a little bit more interpretable here, even though the hex kind of looks cleaner. Is it not going to let me change that? It's not going to let me change it. Oh well. Okay, so we have a finite amount of space in the destination, and we control how much information gets sent in. There's, at least up to this point, there's been no limit on how much information we can pack into a single CGI parameter value. So if we want to just do a quick sanity check on this and confirm that we actually do have a buffer overflow, I can connect to the router and pop open our little HTTP file here, which is where we're kind of doing all of our quick and dirty send a packet over the network work. And we can actually confirm this suspicion. So, alright, so we're connected. Now, if I want to reach this function, it looks like I obviously need that WLANT parameter in there somewhere. And if I want to be able to access, or actually reach this function rather, from apply.cgi, I need to also include this start EPI parameter. And it looks as though the only restriction here is that that value not be null. In other words, that it is present. But if we go back into the function, we notice that the first thing that's being done is comparing the argument that we pass in, the CGI parameter value, which is called start EPI. And it's comparing it to make sure it's 1. And if it's not 1, then don't bother to do any of this. So we also know now that we need start EPI, and that has to have a value of 1 if we want to reach this code. Now the rest is kind of going to be plug and chug. That'll stay the same. And so if we send sufficiently many values, or rather a sufficiently long value for WLANT, it should overflow the buffer that's available in destination here and start trampling all over this saved S0, saved S1, etc. all the way down to saved RA. Now RA in MIPS is the register that holds the return address. So when apply CGI is running, it's making use of all of those registers, right? But then it's going to jump from the apply CGI context into the start EPI context, and then eventually start EPI will exit and execution will resume in apply CGI. So apply CGI basically just needs to record what the current state of all those registers were so that it can pick up seamlessly. So that's what's being done over here. It's saving all of the registers that had meaningful values in it, including, of course, the return address where we need to jump back to in apply CGI once we're done with start EPI, so that it can pick up later. That's the whole idea of saving the values of those registers to the stack. That's what this means. So if we trample all over this, that's going to cause serious problems in execution once we return back to apply CGI. And that's if we just go through and overwrite all of these. If we overwrite the return address, then the processor has no idea how to get back to apply CGI. We've destroyed the only record of where we're at in apply CGI. So what I'm going to do here is just generate, using Python, something like 500 A's. That's overkill. We could probably get away with doing less than 300, but let's just make sure that we properly squash the stack here. And we'll send this over the network. So at the moment, our web server is running just fine. We can just prove that to ourselves really quick. We'll log in. Yeah, there it is. Now, when we send this over, we shouldn't get a response. If we do, we've done something wrong. Because the server should crash. It should crash at the point where it tries to return to apply CGI and it can't, because that address is going to be overwritten with a whole bunch of A's, so that's like 41 in hex. Just 4 of those. So let's give this a shot here. And sure enough, as we see, we get socket hangup, which means that the web server crashed and it's no longer there. So we can satisfy ourselves of that fact just by hitting refresh. And we get nothing. It can try forever, but the web server has in fact crashed. Which means actually I need to restart the router because that web server is not going to come back up on its own. Okay, so now what can we do with this? Well, I think we've done just about as much as we can in this direction just by the use of static analysis, so we're going to have to take the more dynamic route. Now fortunately, we have a debugger included in the GPL here in our tool chain. So I just ran a pretty standard search for everything with GDB, the GNU debugger, inside of the tool chain, and there were a ton of results. But the ones that we'll focus on here are the fact that we have GDB and GDB server present inside of our tool chain, and presumably those will work perfectly on the architecture that the router is using because, well, it's included in the tool chain. This is what the developers used. Now why they would include it in the tool chain is kind of beyond me, but I'm not going to look a gift horse in the mouth. So GDB is a pretty big program. I'm not confident, in the same way I wasn't confident that the big bloated build of Netcat wouldn't fill up the amount of available space that we have in our temp directory. I have a hunch that GDB might do that too, but fortunately we also get GDB server, which is a lot more lightweight and can do pretty much the same thing, provided that we're able to connect to it from our research machine. And we'll see what that looks like in a second. So I'm going to copy this guy into the directory that is being served by our Python server that we've been using throughout. And we'll just check and make sure that it's actually there. Yep, there it is. Okay. And now we're going to copy, or rather download actually, GDB over to the router. Now I've written this script here that is going to automate this process so we don't have to go through the laborious motions of using that POC that we used to originally get the reverse shell. And instead we're actually going to be leveraging the vulnerability found in the previous video, which I like more. It doesn't end up messing up the front end, it doesn't cause any problems to the execution of the HTTPD binary. It's a much more sneaky command injection than the one that we were able to find during the recon stage. So usage-wise, we're just going to specify whatever files that exist in this folder as command line arguments. So we obviously want our reverse shell, meaning that I should probably start up the handler now while I'm thinking about it. I'll start the server too. And so what we'll say here is we want to download the reverse shell and of course make it executable. And we also want to download GDB and make it executable as well. So I'll connect back to the router here. Alright, looks like it's up, and now we can get this running. Brilliant. Okay, so now I'll go over here and look at the help for GDB server. It looks like we have two options. So we can either run GDB server with the, whatever that COM is either a TCY device or host port. Okay, so we would want host port. By default, it'll just use localhost, and we'll specify a port in a second. And we can give it which program we want, so that would be HTTPD, and then whatever arguments. We don't have any arguments to worry about. Or we can attach to a process that's already running using this attach flag. So it looks like the latter is what we want. So I'm going to have GDB server listen on port 4444, which is pretty standard. I feel like I see that a lot whenever GDB is used. And we're going to attach to, oh shoot, I don't know what the process ID of HTTPD is. It looks like it's 60, okay. Cool. So now we've attached to HTTPD and we're listening for connections on port 4444. So I'm going to open up a new terminal over here, which is going to be the terminal where we use GDB. It's just easy to have a designated terminal for GDB and just keep it running. Now, given that we're debugging MIPS here, I can't just use normal GDB. I have to use GDB multi-arch, which you would download in the exact same way. You can just download it using apt-get or whatever. And we're going to specify that we're debugging HTTPD so that it knows that it can load up all of the symbols on our research machine side. I also installed Jeff, which just makes GDB a little bit prettier. You can look that up yourself. It's super useful if you're using GDB. And what we're going to do here is we're going to target remote and then specify the router's IP and the port number that the GDB server is listening on. And when we do that, you can see that we're now hooked in. We get all of our register values. We know what instruction we're on. It looks like there's a SIG trap. I never really understood what that was, but I think it's just something that happens when a remote connection is received. And as we can see, it now says, okay, remote debugging from our IP. Great. Now I want to place a breakpoint on this start EPI function, and clearly the symbol is still there, so I can just say B for breakpoint, start EPI, and then hit continue. And I'll run the exact same experiment trying to get this router to crash, or the web server to crash rather. And it's waiting. Why? Okay, well, maybe something went wrong when we attached to the running process. So what we can do here is we can just kill the current session, start up netcat again, and retrace our steps, just doing things a little bit differently. So this time, we're going to, I guess we only really need the reverse shell. GDB is still on there. Uh-oh. Didn't get the green check mark. That means something went wrong. Maybe we have to restart the router again. Using GDB typically involves a lot of restarting just to get everything reset, make sure that we have a router whose processes are in pristine condition. to get started. It couldn't check it shouldn't take too long. This router gets up and running pretty quick. Yep, there we go. Oh, but GDB is going to be gone. Download that guy again. So there it is. And we've got our reverse shell again. Okay, so first thing I'm going to do is I'm going to kill off HTTPD. Just stop the process. We're going to try to use GDB to, in the first of the two options that we saw here, where you're specifying the program that you want to run and you're going to start running it with GDB as opposed to just attaching to the running process. And I believe I need the full path here. Can't hurt. Alright, there we go. So once again, I can target remote. And there we go, we've got the SIG trap. Our breakpoint is still there, so now we can continue. And oh no, it says remote target exited normally. Darn. Yeah, so GDB server crashed. Bummer. HTTPD is still running though, so maybe I'll kill that off. So the last thing that we can try is just starting it manually. And then attaching to it from there. And we'll give this a go again. Is our breakpoint? Okay. Well, it didn't crash the thing this time. That's good. Let's see if we can actually interact with it. I'll do something simple. I won't even try to crash it at this point. I'll just do a simple GET request. And that worked. Fantastic. Okay, so it looks like if we want to successfully run GDB on the HTTPD binary, we have to first kill off all running instances, start up a new one, and then attach to it, which is kind of weird, but I feel like whenever you're doing this kind of remote debugging thing, it never works seamlessly or in an obviously sensible way. Of course, there is some reason for it, but I sure don't know what it is. I'm just glad that it works. Okay, so now we can actually trigger this breakpoint. And as you can see, we've broken at the very start of Start API. So we are now right here, right at the very start. In fact, I think it'd probably be easy to also have the disassembly in front of us, just so we have the actual instructions that are being run through the CPU at this stage. So if I want to go to the start of this function, it's right here. That should line up with what we're looking at. Yep. Values, everything, awesome. This is another reason why it was kind of essential to have the exact version of HTTPD on our file system for this kind of analysis. Otherwise, these addresses wouldn't line up. Alright, so we've broken at the top, but I'm really interested in what happens after sprintf has been run. So I'm going to scroll down here to where the first printf gets called. And I'm just going to break on this no op here. And I can hit continue, and we should just fall straight through down to this no op, which, if I've done this right, is Oh, that's right before the call to sprintf. We actually don't want that. We want the no op right after it. So I can delete that breakpoint and instead break at the no op after the call to sprintf. Last sanity check to make sure I didn't screw that up again. Yeah, there we go. Cool. So now I'm going to continue, and as you can see, we've stopped on... did it actually execute the sprintf? Not sure. I'll just go one instruction further to make sure I did this right. Yeah, there we go. Okay. So now we're right here. We're right in between these two function calls. And so destination should contain a whole bunch of A's. So now what's the address of destination? You're going to get me, or rather get to watch me struggle with this in real time here. Okay. Guess we can just start looking around on the stack. 50 will do. So this is saying, give me the current status of the stack using the string representation. So ideally we would just see a string with a whole bunch of A's in it. Don't we see other stuff? Where is it? You know what? I guess that this step is kind of unnecessary. The moment of truth will come at this instruction here, where we try to return to apply CGI, because at that point, according to theory, the RA register will be full of A's. So that'll be an even better telltale sign, since I can't remember off the top of my head exactly where we would find the A's once they've been put in destination. So shortcutting this a little bit, make another breakpoint. We can delete breakpoint 3, wasn't it? Yeah. Right, okay. So now we see that registers S0, S1, S2, S3, S4, and the return address. So everything here that was saved from the previous function, which is apply CGI, has been overwritten with our A's. So this is a serious problem. Now, if I go one instruction further, the whole thing should crash, right? Because this is not a valid address, or at least it's very unlikely to be. Like it's very unlikely that there is actual valid executable instructions at the address represented here. So I'll just go ahead and do that. We'll do next I. And we get a warning, yeah, okay. Cannot access memory at address 41s. So now if I hit continue, we should have seen a crash. What's going on? Wow, maybe it was somehow able to recover from that? It shouldn't have been. Cannot execute this command while the selected thread is running. Strange. Okay. Well, we can just quit out of here when in doubt, but this page certainly shouldn't refresh. Okay, there we go. So the reason to go through that step is to just verify that our user supplied data actually ends up in those registers, meaning that we control them. So let's just make note of this. Where are our notes? So I'll copy this guy off, all of it. Yep. Go over to our notes. And we can say that when this request is sent, we have all of this information printed to the screen from GDB. I wonder if there's a GDB markdown skin thing. I guess not. Whatever. Maybe let's call it log just to give us some colors. Yeah, there we go. I like that. So clearly we can see that we control these registers. We also control the return address. So this means that we can likely use this, I'm going to have to restart the router again, to perform what's called a return to libc attack. We can just pull up the Wikipedia page for that just out of intrigue. So this means that you've overflowed a buffer, you've gained control of the return address, whatever that may be. It's going to look differently depending on the architecture. And if you specify an address that is in the executable part of libc, you can use that to jump to system, the system function, which we used explicitly in the previous video to get a command injection. This is just another way of accessing system. So if we want to go this route, what we're going to have to do is to somehow inject the command that we want to execute on system. We need to jump to system after loading the string representing whatever command we want to run with system into register A0, which is the register that is used to specify the first argument that you want to pass to whatever function that you're calling. And if we've done all that correctly, we should be able to just execute whatever command we provided with the same privileges that the process that we're exploiting has, which in this case is root. So that's the theory. Now there are a couple of things that can get in the way here. The first of which is this thing called the NX bit. Actually, this isn't directly relevant. This would only be relevant if we were trying to use shellcode as opposed to return to libc, but it's still an interesting aside. Another way that we could do it if we didn't want to do a return to libc attack is to actually write the opcodes corresponding to all the operations needed to load our string into register A0 and then jump to system. We could do all of that by just writing the assembly, turning it into opcodes, and then encoding it that way. There are a couple of problems with that though. One of them is the NX bit. So basically this means that certain portions of memory are reserved as non-executable. So even if there are valid opcodes in there, they will not be executed just because of where they sit in memory. This is designated as something that you write to, not something that you execute from. So we'll check in a second to see if this is in place or not. But in any case, this is one of the benefits to a return to libc attack. You don't have to worry about that since you aren't actually writing your own instructions into memory. You're just using instructions that are already there. The other thing that could get in our way is something called ASLR, or address space layout randomization, which basically means that every time a process is spawned and all of its dependent libraries and stuff are loaded into memory, the addresses at which those instructions are loaded differs from how they, or rather where they were loaded before and where they'll be loaded the next time that you run it. It's specifically to throw a wrench in something like a return to libc attack, because this attack relies on you knowing where certain instructions are in memory and having those instructions be consistent. They're always there. ASLR makes that assumption completely unreliable. It's going to change every time the router boots up, let's just say. So, at this point we should probably back up a little bit and use this tool called checksec to make sure that our HTTPD binary doesn't have these kinds of restrictions in place. It won't tell us anything about ASLR, that's an operating system thing. But it will tell us whether or not NX is in place and if there's something like a stack canary. So let's make this a little bit bigger for now. You see the whole thing. So we don't have relrow. Oh geez, I knew at one point when I was in school what relrow was. We know we don't have a stack canary. Now we already kind of knew this. So a stack canary is just a specific set of bytes that will be included on the stack, and if it gets overwritten with data, that sends an immediate signal to, I guess it'd be the CPU, that the stack has been smashed, is probably being used in a way that's unintended, and we should just crash to avoid something like an RCE of the type that we're trying to achieve here. We see that NX is disabled, so we could try shellcode here. No pi, I don't know what the rest of this stuff means, but that was the big answers that we wanted to get, the ones that are most apropos. We don't have a stack canary, we don't have NX. But again, even if NX was there, we could probably get around it because we're doing a return to libc attack. Okay. So, continuing a course, we know that we control these registers. We know that we can use control of RA to jump to wherever we want in active memory, provided that those are valid instructions that can be executed. So we need to know where those instructions are. So the next thing that we're going to do is take a peek at the process memory map for HTTPD, which means I now need to connect back to the router. Are we up? We're up. Grand. Okay, so we'll go back here and we'll run our command to put our reverse shell and GDB server on there again. And we see now we have HTTPD on with process ID 60. So now I'm going to cat out the memory map for this process. It's a proc, whatever the process ID is, and then maps. And this should tell us all of the information that we need. So I'll just copy this off into our notes over here. So what this is saying is that the following libraries have been loaded for use by HTTPD, and they're loaded at in this address range. So this is micro C libc. Let's just use libc as an example since we're attempting a return to libc attack. So there are 3 different sections here that are all libc. And it's this top one that we're interested in. So there's this X present here, which means that we can read from it, we can't write to it, we can execute it too. So this is the executable section. This is where the instructions are contained. So system is going to be somewhere in this range. So in order to find out exactly where, we're going to have to use our old netcat trick to exfiltrate this file. So let's go ahead and put netcat on here. Uh-oh. I don't think we got netcat. No. Why? Is HTTPD down? Strange. Looks like HTTPD's down. I guess when in doubt, just restart the whole thing. Which means I'll have to kill nmap. I guess I don't really care. Come on, where is it? There it is. Okay, so before anything else, I'm going to download everything. Is our handler still there? It's not. Alright. So now we'll run this. We see we just grabbed our reverse shell, we grabbed GDB server, we grabbed netcat. Wonderful. So now we have everything. And I want to grab this file. So once again, I will run netcat with the L and P flags to listen on port 8080. And we're going to send over libc. So now over here I can connect to the router on port 8080 and redirect the output to libc. Alright, so it looks like that process is done. So, oh wait, I might have messed it up by typing stuff in there. Rats. Let's see. Nope, looks good. Alright, so its size ends in 72. Probably a little bit too paranoid here, but Just want to make sure we got the exact file intact. We did. Okay, so we got all of it. Great. All right, sweet. So what I'm looking for is the address of system. So I can go through each entry and like the output of readelf or something like that if I wanted to, but I just want the symbol. So I'm going to use nm with the GD flags to do this. And we've got a bunch of stuff. Okay. Where is system? Screw it. There it is. Okay, so it is sitting at offset 25,430. All right, so I'll copy that. Cool. Oh yeah, we grep for system. Why not just be thorough here? Okay. So we also know that the executable section here starts at this address. So if we want to get the address of system, that's going to be at this plus the offset here. And of course these are both hex, right? So I'm just going to use the calculator that comes with Windows here to actually perform this calculation. And I get this address. Great. So we can be pretty sure at this stage that that's the address of system in case or unless we've done something wrong here. Okay, right on. So now we know where system is. We also, of course, though, need to find some sequence of instructions that's already in memory that'll allow us to jump to this system, because it's going to be no good just to write this directly to the return address, because whatever value is in A0, whatever the argument to system is going to be, it's not what we want. It's not a value that we control. So in order to do that, we're going to have to use something called a ROP gadget. ROP is return-oriented programming. It's a way to, once you've hijacked control of execution, how you jump around to different sequences of instructions in memory that they themselves include jumps, so as to do various operations and set up whatever you're trying to do as part of your exploit. Typically, it's to invoke a call to system. So, in order to do that, I'm going to use this tool called Robber. Although I do not want the command line interface that comes with it. I just want to use it as a normal command. So there are a ton of options here, but what it does is it'll skim through a binary and pick out every chunk of instructions that will do something, do something, do something, jump to somewhere in memory. That's a ROP gadget. So if I just run Robber on libc, you can tell I get way too many results. Way too many results to work with. So instead, what I'm looking for here, how we'll pare this down, this will just make it really explicit what we're looking for out of our ROP gadget, or gadgets. It may take more than one. So the first thing that we need to do is we need to load our command, which is a string, into register A0. Okay, that's the first thing that we need to do. We need to set up the argument. The second thing that we need to do is jump to system. And in theory, that's it. So how are we going to load our command into A0? Well, we know that we can send a whole bunch of data via our WRT CGI parameter and have it end up on the stack. So what if we expanded our payload here to include some command that we want to run? I mean, we could make that, well, we can just reuse the command that we used previously, because we know that'll work. And if we've done that, I mean this won't work as is, but we put something else before it, something to set up all of this jumping around memory. And then what if we just load into A0 the address of wherever this ends up on the stack? That seems like a good idea. Okay. So now we're going to back up a little bit and we're going to figure out, well, exactly what data at what offset ends up in S0, S1, S2, S3, all these registers that we control. So like how much stuff before we get to our important stuff, like our command and our hard-coded addresses, do we need to provide in order that our payload lines up with that space on the stack that we control? Or I guess we control all of it. But how do we make sure that our intended values end up in the registers that we want to control? So in order to do that, I'm going to write a little script here that's going to generate a pattern that's not just all A's, because all A's in this case are created equal. Like I can't distinguish that A from that A. It'll be hard to work out where our relevant offsets are. So I'm just going to write this quick script that I'll just call generate pattern. This is going to be a Python file. And I'm going to generate a long string of characters that come in sets of 4, 4 bytes, 32 bits per address, that will let us figure out what the offset of our various hard-coded addresses are going to have to be to make sure that they end up in those registers. So I can just say for, I don't know, character, probably going to want to use more than just letters here, in range, let's just use ASCII. Why not? So the first ASCII character that's not like, some control sequence thing or on principle is the space, I believe. All the way up to the last one, which is the squiggle, or tilde. I want to print out all of those in bunches of 4. Oh, of course, those are just numbers. Whoops, we want the character representation. We also want it to be all on one line. Okay, there we go. Actually, I really don't like the space in there. I want them all to be printable. So the first one after the space is the exclamation point, so we'll start there. That pattern's still going to be long enough, right? Okay, cool. So we'll just save that off to a file. so we have it. And so now we can figure out what the relevant offsets are for the values that end up in each of those registers. Oh wait, I just remembered. These are URL parameters, so a lot of these characters are going to have to be URL encoded, otherwise they're just going to get rejected. So, in fact, we actually have to reuse that URL encode like mini script that we use to encode the command. I guess the best way to do this is just going to be to pipe the output of generate pattern straight into URL encode. There we go. That'll work. Alright, so are we still running here? Doesn't look like it. Waiting. There it is. Alright, we're up. Sweet. Okay. So let's get GDB started again. There it is. And why don't we include netcat too? Can't hurt. Temp, GDB server. Oh wait, before we do that we need to kill HTTPD, get it started again, and then grab its process ID. Okay, so let's hope that this works again. Alright, so we want to set a breakpoint on the return instruction, which is this guy. And now we can continue. Yep, server still works. Okay. And there we go. Alright, so now we can start figuring out what the relevant offsets are for S0, S1, S2, S3, S4. using injected there in a very loose sense. Okay. So now I'm just going to search for caret and 3 underscores. Just cancel that at this point. And is that going to tell me? Yeah, there we go. Okay, so that is at column 252. Well, that doesn't look right because it's halfway through like a multiple of 4. That's weird. Maybe this is indexed at 0, or at 1 rather. It is. Okay, so we just need to subtract 1 from whatever the index is. Okay. So it's going to be 247. Yeah. That. 247. Which means, given the order in which these are saved to the stack, and then thus read back into the registers, it looks like we can just add 4 to each one for these S's. So that's going to be 51, that's S1, 55 for S2, 59 for S3, and the last one is 263 for S4. And we'll just sanity check that because we can. Yep, 264 minus 1 is 263. Okay, now what about the return address? That's going to be DEE. So that's going to be 271. Right on. Okay, so now that we know, once we figure out all the memory addresses that we want to actually place into these registers, we now know exactly where we need to put them in our payload. Okay, phenomenal. Now, let's see what's next. So, we know where system is. We know that we need to find a ROP gadget that is going to load whatever value is in one of these registers that we control into register, I believe it's T9. It's what you use to execute a jump to a function. Yeah, so this is just a MIPS thing. T9 is always where the address of a function gets moved to, and then you just jump to the address in register T9. That's how a function gets actually called. That's how the jump gets performed. So we're looking for some gadget that includes the instruction, or an instruction similar to move into register T9 the value in register S1 through, or rather 0 through 4, just to reg exit there a little bit. That's what we're looking for. We also know that the gadget must include a move instruction, or something similar. There are a couple ways to load values into a register that will move something from one of the S registers that we control into A0. Alright, so let's get about that. Let's try to find ourselves a ROP gadget using Ropper. So I can use this search flag to specify a pattern kind of like this to kind of narrow down that massive list of gadgets that we have that we're looking for in the libc library. So I'll just start with A0. We need it to satisfy both of this criteria, but I believe I can only search for one. Now if I do that, you can see we have significantly less results, but this first instruction in each gadget is a move from register SX to register A0. So all of these satisfy the second criteria. Now let's see if any of them also satisfy the second one. You can see that all the jumps are to register T9, but a lot of them are being loaded directly from either an offset from the, what is that, the global pointer, or maybe a few from the stack perhaps. Yeah, it doesn't look like it. So what we're going to do here is we're just going to grep for a move instruction involving T9. No. I saw a few. What the heck? Oh, you know what? They're using ANSI codes to give us a nice colorized output. So maybe I believe that for Ropper, if you just say no color, it'll just give it to you without the ANSI codes. Yeah, there we go. Okay. So here we have a move from S7 to T9. There's V0, 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 V0. Okay, darn. So even though this is an S register, it's not one of the ones that we control. We don't control S7. So if we're going to find a gadget that fits this criteria, we're going to have to look elsewhere. Now, fortunately, there are a whole bunch of libraries that are loaded up for use in the running of HTTPD, and so all of these are going to be available in the process memory space. So I guess we just have to pick another one and hope for the best. I happen to know that expat is pretty big, so that would be a good one to look at next. Whoops, I needed that. It's our netcat listener. I mean, we're going to have to restart everything anyway, since that web service crashed and we've probably lost our shell. Okay. So I want the rev shell, I want GDB, and I definitely want netcat. Oh, but that's not going to work, of course, because we have to connect back to the router. And we're back up. Alright. Server's running, listener in place. Let's go. Sweet. So, once again, netcat. Listen on port 8080, and we want expat. So over here we'll do the same thing that we've done before. When exfiltrating files. So the size of expat ends with 320. Sweet. All right, so same thing again, except we're not looking in libc, we're looking in libexpat. So now we see we've got a ton. This is great. I don't really want to look through that manually, so I'll just say s something. I believe this is a regular expression, so we can just output only that. Uh-oh. Maybe it's not. What's happening here? Oh well. Maybe we won't get clever with it. We'll just look at this by eye. So that's V0, 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 V1, V0, V0, T0. Not sure if we control that one. Doesn't look like it. V0, 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 V1. There's another T0, V0, V0, V0. All of these look like V0s. Yeah, okay. Well, no luck. So, on to the next one. libcrypto is pretty big, so is libSSL. Let's do libSSL next. Alright, so that one exited cleanly. Now we have libSSL. I'll just verify it for size, although it's probably becoming unnecessary at this point. That's the right size. Alright, wonderful. So Ropper once again, except this time we are digging through libSSL. And so here we see pretty close to the top, we actually do have an instance where we're moving a value that's in register S0, which we do control, into T9 and then jumping to it. But that one's not going to work because it's only using S0, so those values are going to get messed up. What about this one? So this one is move the contents of register S0 into register A0. Okay, that's an automatic. And this one is move the contents of register S1 into register T9 and jump to it. So that's exactly what we want. So it looks like this. Actually, there are a couple of options here. Might as well just grab all of them. So this is going to give us exactly what we want. Let me separate this out a little bit here just for good measure. Grand. All right, so we'll start out with this guy. Now, we need to know exactly the address of our gadget in memory. So that's going to be the offset from 0 when we look at the library in isolation, plus, rather, wherever it gets loaded into memory when being used by HTTPD, which is this value. Yep, that's the executable section. It is. Okay, good. Oh, I should check and make sure that when we were doing this calculation for system, I actually did use the start of the executable chunk. I did. Wonderful. Okay. So far, so good. Just get out my calculator again because I don't want to have to do that in my head. Cool. I don't know about you, but I always prefer when my hex is lowercase. That's the same value, right? Yep. Cool. So now we know that we want S0 to equal this guy, which is the address of our gadget. Or, excuse me, this is not the address of the gadget, this is the... Oh, no, it is. It is. So this is not going to be S0, this is going to be the return address, because we want to jump to the gadget. That's right. This is why taking notes is so essential, because it's so easy to just get mixed up with all these different registers and addresses that you're working with. I mean, this is literally what my scratch paper, my little notepad text file looks like. And then the address of system, that's going to have to be in S1. Okay, so S1 is going to be the address of system. And then the last one is going to be S0. So this one's kind of tricky, because since we are ultimately going to have to, I mean, the only way that we can inject our command, at least without finding a totally different way of doing it, is to write it to the stack. We have to figure out where the stack is. So stack address of command. Let's see, where's the stack? It's gotta be this, right? This is reserved for stack, I'm sure. And because it's writable and executable, that'd be another tip-off that NX is not enabled. Okay, so it's going to be impossible just to figure out without using GDB to look at it where exactly our command is going to end up. But let's start getting just a little bit more deliberate about how we craft our payload here. I think we probably used our little REST client that's built into VS Code to the extent that we can. So let's start thinking about it. So our payload is going to have to be a bunch of just padding, I guess, up until the point that we start getting bytes that are going to be loaded into registers. So we can say here that Well, you know what? I'll just do this in Python. That seems smart. I'll just call that POC.py. We probably reuse some of the functionality here, can't we? Just copy all of this. Probably delete all of it too, or a lot of it. We don't need command line arguments. We don't need handlers. We don't need my IP. We do need the target URL, and the timeout can't hurt either. So the payload is going to be different, that's for sure. In fact, this doesn't even need to be a function, does it? And it's not a command, so we'll remove that print. And we're expecting this not to return a response at all. Trim that down. Okay, so the payload is going to be, some byte that we don't care about. Let's make it something really easy to see as being meaningless. What about, see, my instinct is to use null, but of course we can't use null because that'll just terminate it as soon as it gets transferred into a string. I don't think you can send null bytes over HTTP? I'm not sure. I don't think so. Let's just use 22. That's a single quote, or a double quote, I believe. Could be wrong. Don't have the whole ASCII table memorized. But we know that that's going to have to be 247 bytes of just padding. And then what do we want? Then we want to include our value for S0. S0 is, well, no, that's unknown. We're trying to figure that out. So for right now, I'm just going to put 4 question marks, just to, I guess, pay lip service to the fact that we don't know what that is going to be. And then we're also using S1. And S1 is the address of system, that's this guy. And I believe we have to reverse the order of the bytes here. Yeah, we do. Okay, so the first byte is going to be 30 F4 then DE and then 2A. That'll be really embarrassing if this is one of the cases where you don't, but pretty darn sure you do. An endianness thing. And then what's the offset for RA? So this has already been accounted for. So we're going to need to put RA whatever 271 minus 255 is, which would be 16. We can just make this a constant. I like a good self-documenting exploit. And now we can put in the address of our gadget, which is going to be A0 6D CF 2A. You know, I'm actually going to self-document this a little bit further. Because it'd be good to have some knowledge in our code here of what the registers are. So this is going to be S1. Yeah, so here I'll just say S1 is equal to this guy. And then this will be RA. And then whatever comes after in principle doesn't matter, because we're already stomping all over the stack, so we might as well just include whatever we want. So we can make this whatever command we want. So let's put up here, we'll make the command a constant. And what command did we decide that we wanted to run? We decided that we wanted to do wget, right? So I'll just write this out here. Wget to the temp directory. Some file. Doesn't really matter which file this is. But it would be nice if it was a file that actually existed. So maybe I'll just create like a tiny file called X and we'll just use that. Single byte file, nice and tiny. And yeah, there it is. Okay. Restart this server. Oh, that'd be bad. I want to get it from my host. And we're going to have to quote this. In fact, we should probably quote the entire thing, I realize now. So the payload itself got to line up as equal signs. Is going to be just what it was before, but URL encoded. Okay. I like that. So now we get to restart HTTPD. And then restart it. Hopefully we can just make this all one line. Yep, there we go. Did that work? It did. Okay. Attach to it with GDB. and we'll connect. Uh-oh, did that mess it up? Nope. Okay, good. Uh-oh, what happened? Huh, it crashed. Like, totally crashed. But it restarted on this end. Okay, so it looks like we'll still be okay. Yep, right on. Ah, rats, I shouldn't have hit continue. I should have set my breakpoint. Bummer. I don't know, can I do this? Ah! Oh no, I might have messed it up. Rats. See, it's a bummer that whenever you hit Control C inside of this reverse shell, it just kills the entire thing. It doesn't just terminate the process you're running, you know, from the reverse shell. Oh well. So I just need to download the reverse shell again. Of course. The server process also got messed up. See, if people understood just how long hacking takes, I feel like the movies would probably be different. Alright. Handler, server, sweet. There we go. Oh, but of course now I don't have GDB, do I? Why doesn't that work the second time around? Oh well. At least while we're waiting for that router to boot back up, I can make sure that I set my breakpoint where I want it. Which is right here. Alright. So we'll connect back to the router. And I'm going to make sure to grab both of them this time. There's GDB server. There's the reverse shell. Great, now I have both of them. Sweet. So same thing again. Kill off HTTPD, start it up, and grab its process ID. That looks right. Uh-oh. Huh. Weird. Whew. There we go. Now we can run our poc.py. So unless I've made a mistake here, this should send our payload over, and we can verify, well, two things are valuable about doing this at this point. We'll know that we've got everything right in terms of just how we calculated the offsets and how we've translated those into a program. And we can also do some poking around the stack to see where our payload actually ends up, and that will tell us what to put right here in S0, which right now is unknown. All right. Well, that's not good. What did I do wrong? Is it at least working? Yeah? Now that's very weird. I don't know. Well, nothing to do here other than to restart, try again. But maybe we'll set this up so that alternatively we can have like a benign payload. So what's like a sensible value for that WLAnt? I don't even know. Maybe we'll just put a couple of semicolons just so we cause it to fail, but we don't cause the program to crash. And you know what, now I'm paranoid. Now I'm going to start a packet capture. Just to make absolutely sure this is actually working as we expect it to. Okay. Oh, for heaven's sakes. I forgot to start it with GDB. Now just making absolutely sure that we have our breakpoint in the right place. D74. You know what? I'm also, just because I'm paranoid now, I'm going to also put one at the start of the function. And now we can continue. So I'll just restart that packet capture. So when this happens, I always assume I've made a stupid mistake. Maybe going over here to our POC file, which we used earlier. Oh, okay, so that works. Oh, you know what it was? I wasn't including, as part of creating the payload, the URL parameter setup part. Ay, ay, ay. Okay, well, now we know. So we can delete that. That's another thing about hacking, all the dumb mistakes that cost you time along the way. Cool, I feel a lot better about that now. But naturally we're going to have to restart the whole thing. Alright. Alright, everything's set up. There we go. Alright, so yeah, we still want a breakpoint on the start of the function. Just satisfy the paranoia even further. And another one on the return address, which is right before, ideally, we'll make that jump to the gadget. And everything will be right except for the fact that the argument is going to be bogus. Oh, yeah, right. Beautiful, there we go. Alright, so now we are, yep, at the start of start API. Okay, so now I can continue. You'll notice for, I don't know, for some reason we've got some of those double quotes which are unused bytes in the temporary registers. Not quite sure why that is. But we'll continue, and now we're at breakpoint 2. Okay. So, at this point, we should have the proper value in RA, which is the address of our gadget, which is this thing. So let's look at RA. Uh-oh. RA does not contain that. What about S0? S0 is starting somewhere totally different. Very weird. Well, let's just continue, see what happens. And we get a failure. And the target disconnects. And this thing hung up too. Okay, so that wasn't at all what I expected. But I'm kind of interested to pick this apart and see exactly what went wrong. So, is this at the first or the second break? Second break. Okay. Well, while we're mulling this over, I'm just going to restart the router. And I guess we are already debugging, so we'll just step through it with a bit more care, perhaps. And set some more breakpoints. So I'll set a breakpoint right after sprintf gets, actually it's not this one, it gets done in two places. Strange. WL rate only gets used once. Maybe we'll just pivot this whole thing to using WL rate. Kind of simplify matters. Instead of using WL ant, I'll use WL rate, because they're really, if you look at the logic here, if WL ant isn't present, it's just going to skip that entire block. If WL rate is, then it's just going to execute this one. And maybe it could have something to do with the fact that it's being written twice. I don't know. But in any case, it'll make our entire setup slightly simpler. So that router's going to be back up now. And we're back. Maybe it has something to do with the fact that I'm quoting the entire payload. It shouldn't, but we're trying things here, so why not? It can't hurt. Maybe instead of quoting the entire payload, I'll just quote the command. Or actually, it's not even a command. I'm in the command injection mindset. It's the, no, it is the command. Yeah, so I'll just quote that. Quote meaning encode for a URL. Okay, so far so good. Still got my breakpoints. Maybe I'll just step through the function. That'll help. So once again, kill off the running version of HTTPD. Process ID. Now, any more breakpoints that we want? Because stepping through it, I realized, can cause a few problems. I think we're probably going to want to set one here, right before this function gets called. So, like right here, maybe? Try it again. All right. So at this stage, nothing's happened. I can just keep going to the next breakpoint, which is in that no op. Great. Okay. So S0 is nothing. That's to be expected. Nothing's happened yet, but I do want to know what the value is at the destination. Looks like I need to look back quite a bit for that, so we'll just say SP minus 140. Well, that looks like something meaningful. There we go. Well, here's the start of our payload. Looks like it's at this address. I always forget exactly where the stack pointer is. Maybe if we dump the next 100 starting here. Ah, here we go. Right on. So if I run the same GDB, well, no, I need to take out the 100, don't I? Okay. Good. Well, at least that answers the question of where our payload winds up. We now have the address. It does not answer the question of why we didn't see the intended values in our S variables. Oh, actually, yeah, there we go. Huh. I have no idea why it worked that time. Well, okay. Let's take a peek at this. So it looks like we have some kind of off by one error here because S0 is not totally filled up with question marks as we would like. It looks like we just went one too far, or not far enough. All the endianness is kind of mixing me up here, but looks like S1 is also just off by one. So perhaps we need, yeah, I think we just need to push this along one more. So let's try 248. And we'll tear it down, do it again. Now the only breakpoint that I want, now that I'm confident that I've got a working POC right here, well, almost working, is this final breakpoint, which is the jump back to the return address. So I'll connect back to the router. Kill all HTTPD and restart it. Now we've got everything lined up. Beautiful. Okay. So here's S0. Which you can tell has all of our question marks in it. You know what, I'm just going to benchmark this with like copying it off and saving it so we have it. Yep, okay. Cool. Now, this means we have everything lined up properly. And so we can start figuring out how to find what this value ought to be. Now, in the notes from when we looked at this last time, it said that my string appeared at this address. And it still does. Okay. So, now we need to figure out where the wget part starts. So it ought to be whatever, let's see, it would be WL rate, or actually I can just do this in Python really quick over here. So it would be the length of WL rate space, because that's this part of the string. So whatever that is, plus the length of my payload, which is going to be 248 plus, oh, so that's why it was messed up. Again, it was just me being shoddy and careless. This needs to be 16. All right. Well, there's another blatant mistake that we're just going to need to start over if we want to get this remotely right. Yeah, see, that's definitely not our return address. All right. Well, I'm not a perfect human being. At least now we know, though. connected again. Alright, so we'll just double check our POC here. Yeah, we still got the question marks, but that's fine because we're going to sort those out with this next run. Now RA looks correct. Let's see, this ended DA0, DA0, perfect. S1 is exactly what we want it to be. Alright, fantastic. And then if I run this again, we should see our command that should be correct. Yeah, there we go. Right on. Alright. So now it just becomes a matter of figuring out just how much we have to add to this value in order to find the address on the stack of our command. So it's going to be that plus whatever the length of WL rate is. This is where I'm going to use Python. Plus 248 plus 4 plus 16, it's 24, plus another 4, that's 28. And that should do it. Alright, 248. Now what's that in hex? Okay, plus whatever this is. Sweet. So now we can fill this in. We can say S0 is going to be string representation of that address, which is going to be 34, followed by 2F, followed by FF. followed by 7F. Sweet. And if we've done this right, our gadget, which, where did I put that? I put that in the notes somewhere, didn't I? I better have. Yeah, there we go, it's that, this one. We will move the address of our command that's on the stack into A0, move the address of system into T9 and then jump to it. And we got here by overwriting the return address. Just a quick recap there. So hopefully for the last time I will restart the router. Reset our handler here. Okay, breakpoint in place, and now we're continuing. And I can run the exploit, which looks finished. So, here we go, we've hit the breakpoint. And as you can see, we're looking ahead, we can see our gadget moving S0 into A0, S1 into T9. Now, is this address correct? It is. Wonderful. So that calculation went okay. Phenomenal. Alright, so if everything's been done right, we should see a GET request for that little single byte X file when I hit continue. And there you have it. So, to recap, we were able to find a vulnerable call to sprintf. We then were able to trigger a buffer overflow and cause a crash. And then we used GDB to figure out that not only did we cause a crash, but we controlled the return address and several key registers. We then found a sequence of instructions that loaded the value from a register that we control into the argument register A0, and loaded the address of a function from a register that we control and jumped to it. We then figured out where the system function exists in memory and where the pattern of bytes that we had written to the stack existed in memory. And then we put it all together and were able to successfully execute arbitrary code over the network, thus pwning the device. Now, I'm sure that there are more vulns of this kind or of a similar nature in the web server. I just didn't have time to look into it. I had actual work to do. But I'd like to leave you with, I suppose, an open question. In the first video, we didn't look into the UPnP attack vector. But I'm sure that there are probably some vulns in there, even if it's just a denial of service. So why don't you go ahead and buy the router off Amazon, it costs like $30, and have a look at it. see if you can find anything. And if you do, please shoot me an email at jesse.chick@trellix.com. I'd love to hear about it. Alrighty, hack the planet.